Last time I talked about stress transformations, re-expressing a stress tensor in a new coordinate system. You're late. Now I'm not handing back your quiz. I don't have them, so I can't hand back any. Stress transformations. And so let's do two examples. And remember, the way that worked is find a rotation matrix Q that takes vectors from the old coordinate system to the new coordinate system. Then the stress tensor in the new coordinate system is equal to Q times the stress tensor in the old coordinate system times the stress tensor, rotation matrix, times the old stress tensor times the transpose of the rotation matrix. Okay, so let's do two examples. One will hopefully convince you that this works, and then the second one will just be an example working on the calculation. Okay, so let's say that in this coordinate system, the stress tensor at a point is 5, 1, 2, 1, 0, negative 10, 2, negative 10, 3, and this is all in megapascals. So first, we're going to draw the stress element. Then we're going to transform this stress tensor into a new coordinate system that's rotated 90 degrees about the y-axis. And then we're going to draw the new stress element. And we're going to be able to see that the stress tensor we got is the right one because those stress elements are, rotated 90 degrees from each other, and so we can, so the corresponding faces all have to have traction vectors in the same direction. You know what I mean? Okay. So the stress element no whispering.
No secrets.
Yeah, there's no secrets in this class. We have to have an open atmosphere. Okay, so if this is the coordinate system, the usual coordinate system, we have 5 that way, 1 that way, and then that one has to match. Positive 2 that way, and then that one has to match. And then 0y yz is 10 this direction, and that one has to match. And then z is positive 3. Okay. So there's the stress element. So now we want to use the rotation matrices to re-express this in the new coordinate system. We want to rotate the coordinate system positive 90 degrees about the y-axis. So the rotation matrix is cosine of 90 degrees, negative sine of 90 degrees, because remember the y-axis always has to be the difficult one. 0, 1, 0. And then positive sine of 90, 0, cosine of 90. So that's 0, 0, 1, 0, 1, 0, negative 1, 0, 0. So that means that Q transpose is all the columns here are rows in the transpose, so 0, 0, 1, 0, 1, 0, negative 1, 0, 0. And so the stress tensor in the new coordinate system is Q times, where was that original stress tensor? I think I gave it, didn't I? Whoops. And then multiply by the rotation matrix transpose. Okay, I have not done this, so let's pop. I get, tell me if you get anything different, 3, 10, negative 2, 10, 0, 1, negative 2, 1, 5.
He said it was wrong.
Okay. So that doesn't mean too much yet, but now let's draw the stress element. So I'm going to draw it in this orientation. And let's see. We still have the y-axis going this way because that's what we rotated around. If you rotate, so we rotated positive 90 degrees about y, so this way, which means the x-axis that used to be that way is now pointing back. And the z-axis is pointing this way. Okay. And what?
I suppose you do y is coming at you and you rotate counterclockwise. Positive.
Well, the y-axis, we started with the y-axis up, so our thumb is in the direction of y, and then our fingers do the rotation. Okay, so in the x direction, we have a positive 3. So that means on this, the positive x face is the one into the page. And so we have a force going into the page there. And on the negative x face, that means we have a force coming out of the page this way. It's not a force, it's a traction vector. Everyone follow what? So on the positive face, it's in. But that means on the negative face, it's out. Because remember, all the traction components on the negative faces are all equal and opposite to the positive faces.
I thought that the x-axis, when it's positive, it's coming out the face.
It's going out of the face. When it's positive, it's going out of the face. So on the positive x face in the back, there's a vector going into the board. And that means on the negative x face, there's one coming out of the board. Then, let's see. There is, so we're still on the positive x face, and now there's a shear in the positive y direction. So on the obscured face, it's pointing up, which means on this face, it's pointing down with a value of 10. And then in the z direction, it's negative 2. So on the obscured face, it's 2 going this way, which means on this face, it's 2 going that way. And let me draw in these matching shear elements that we know we have to have because of moment equilibrium. And now on the y face, let's see, we already drew the 10. We have no normal component. And then in the z direction, we have 1 in the positive z direction. So we have 1 like that, and therefore we have 1 like that. And then on the z face, we've already drawn the one in the x direction, in the negative x direction. We've already drawn the one in the y direction, and then we have 1 coming out of the face with a magnitude of 5. Okay, so since we're talking about the same point, all we've done is re-express things in different vectors. What we've drawn here needs to match exactly with what I drew before we did the transformation. I hope it does. It does. Isn't that cool?
So you changed the axes.
So yeah, I changed the coordinate system it's expressed in. It changed the numbers all around. But when you think about the physical thing that those numbers represent, they match. Because it's still the same state of stress. Well, most of the time we're not going to do it at 90-degree angles. So it'll be more, so I'm going to do one now where we have like a 30 or a 30-degree angle. And then you can't look at it and tell anything similar. But
You wouldn't be able to just like draw your little mini coordinate system where you don't draw that 30 degrees.
no, you can't do that because two things change when you rotate the coordinate system. You're changing the orientation of the face, and you're changing the meaning of the traction components. And so it's more complicated to try to sort it out than like with a vector or something. But when you do rotations at any 90-degree chunks, you can look at that stress element and they all have to match up. Any other questions about that? Okay, so let's do an example at a more general angle. So let's say we start out with a stress element in our usual coordinate system. With 50 MPa and then 10 MPa two MPa there and there, and 20 MPa there. And we want to draw the stress cube I was going to erase that what. Okay, so draw the stress element in a coordinate system rotated plus 30 degrees about the z-axis. So our new stress cube is going to be something like this. Okay, it's just rotated 30 degrees about the z-axis. Okay, so the first thing we have to do is come up with the stress tensor for this. On the x face, we have no normal. We have a negative z of 2. Whoops. Why did I do z? For y, we have, okay, no y, and then negative 2 for z. On y, we have nothing for x, negative 50 for y, and then 10 for z. And then we can use symmetry for those two, and then we have negative 20 for the normal stress. A rotation matrix, we're going from this to this, where that's 30 degrees. So Q is equal to cosine of positive 30, sine of positive 30, 0, negative sine of 30, positive cosine of 30, 0, and then 0, 0, 1. So that's 0.866, negative 0.5, 0, 0.5, 0.866, 0, 0, 0, 1. And so then Q transpose, what were columns are now rows. So 0.866, negative 0.5, 0, 0.5, positive 0.866, 0, 0, 0, 1. And then the new stress tensor is equal to Q times the old stress tensor times Q transpose. And if you punch that in, you get negative 12.5, negative 21.65, 6.732, negative 21.65, negative 37.5, positive 7.66, then 6.732, 7.66, negative 20. Yep. Okay, so we have, so there's the x-axis is that way, the y-axis, that way, and the z-axis is this way.
Don't have to worry about when we see all the faces that we're dealing with.
In this case, we see all the positive faces. It's much more of a nuisance if you're looking at negative faces because you have to think about equal and opposite components and stuff. But okay, so the stress tensor says on the x face, our normal stress is 12.5. Our y traction component is 21.65, and there's a matching one up here. And our z stress component is positive 6.732, and there's a matching one here. Then on the y face, we already have the 21.65 drawn. We have a compressive stress of 37.5. And then in the z direction, we have a positive 7.66 and a matching one there. And then on the Z face, we've already drawn these two, and then we have a compressive stress of 20. And you can see in this case, you know, like in that last example, because we were doing everything at 90-degree angles, we could visually, you know, we could look at it and tell whether we had our answer right or wrong. When you get in these off angles, there's nothing you can do about it. You just have to make sure your calculation is right. Any questions about that? It has to do with the fact that okay, so think about it like this. Okay, so why do we have to use the transpose? Typical Kenny. Okay, so yeah, exactly. Now you're a YouTube sensation. So think of the Q vector. If you left multiply a vector by the Q vector, it takes vectors from the old coordinate system to the new coordinate system. Q transpose takes vectors from the new coordinate system back to the old coordinate system. That's what the transpose of a rotation matrix does. It reverses it. They're inverse matrices of each other. Okay, so think of the stress tensor in terms of as a way to calculate traction vectors. So remember, the traction vector is equal to the stress tensor times the outward facing normal. Okay. So, oh boy. So what we want to do, so we're thinking of so we want to I'll have to think about that and get back to you. You can think about it this way. I know that, but I'm okay. Yeah. Yeah, right. Partly because of that, and then there's other reasons. Yes.
Since our classes are short, if you don't want to use up class time explaining this, you could just post the video on YouTube explaining this.
That's true.
So you could just look at
Yeah, that's true. I could do that, but that would take extra work for me. Okay, so next time, I'll get back to that. Okay, so one of the reasons, so the next topic. one of the main reasons that we want to do these stress transformations is to express the stress tensor in the principal coordinate system. In the principal coordinate system, the only stress elements are normal stresses. So there's no shear stress. And the three, so then you have three in general normal stresses, and two of those are maximum values of the stress. So let me say those are, one is the maximum normal stress possible. And so let's call that a maximum tension. One is the minimum normal stress possible. So that would be the maximum compression. And then a third normal stress that's in between those two. What did I say? Yes. This should say minimum. Okay, and then there's a third one that isn't as useful, but there's a third normal stress in between those two. Knowing that maximum and minimum stress turn out to be really useful for predicting failure of a material. And they make it easy to calculate another thing that is probably most of the time more useful for predicting material failure. They make it easy to calculate the maximum shear stress. Okay, so that's why this principal coordinate system is useful. It's useful for quantifying how likely something is to break. Yep.
So that kind of means that, normal stresses, knowing about them is like directly related to shear stresses.
Yes, that's right. Yep, there's a real simple algebraic relationship between so if you tried every possible coordinate system and you found the maximum normal stress out of all those possibilities and the minimum normal stress out of all those possibilities, there's a simple algebraic relationship between those and the maximum shear stress you would find anywhere. It's interesting, surprising that that's the case, and it's a nice fact. It's really useful. Old people, okay, so this is important. You may have a future professor who calculates the principal stresses using what's called Moore's circle, like named after Jay Moore, I assume, a comedian. That was a real topical joke like 15 years ago.
This is the old way or the new way?
This is the old way. You may have a future, most likely old professor. Their gray hair and slumped posture will give them away, who calculates principal stresses using Moore's circle. And so if you hear this term in a class, you need to think to yourself, I don't do it like that. I do it this other way. Okay? We will do the same thing using an eigenvalue eigenvector calculation. Okay, and so the benefit is your calculator does this. You don't have to. The Moore's circle way is like it's a graphical approach where you use, you draw these real careful circles and then you measure the angles and do all this stuff. It's really cool how it works, but it's sort of nicer to just punch something into a calculator. And I'll talk about how that calculation works. But the main thing I want to say is if that ever happens, like you're at the U of Minnesota or whatever, and someone mentions Moore's circle, and say you're in like a helpful mood, you should say, so if a professor in the future brings up Moore's circle, you should say, I learned to do this, and I want you to say this word for word. I could write you a note and pin it to your shirt if you want, but I learned to do this as an eigenvalue calculation because they make electronic digital calculators now.
What are the odds that he or she's going to just keep you out of the class for that?
For saying that, quite high. But in my opinion, it's worth it. You'll have to judge for yourself, I guess. What? Yeah, that would be great. I would really like that.
If you don't want them to know it's you, though, just write it
Yeah.
How recent was this discovered that you can use just eigenvectors?
Well, I mean, it's forever ago. But the thing is, before...
So it probably means that they lived before forever ago.
Well, no, it doesn't mean that. It just means that before you held calculators that could do eigenvalues, like calculating eigenvalues by hand is a real nuisance, you know? And so Moore's circle, like if you're just sitting there with a piece of paper, is a quicker way to do it. But since on your desk now is this thing that tells you eigenvalues and that's the end of it, and MATLAB does it and whatever, there's no benefit to doing it with Moore's circle anymore. This gives you all the information that Moore's circle does faster and more accurately. So that's what we're going to do.
Can you post something on detail about Moore's circle if somebody wants to actually learn it?
I can point you to a book. I don't think I'm probably going to.
Should you write down the URL for Google right there?
Yeah, Google.com. Reference, a footnote here. Okay, so here's the idea. So here's the setup for the eigenvalue problem. Have you guys had classes where you've done eigenvalue calculations before? Probably in math classes that you've talked about it, right? Calc 4, okay. So
You can refresh it.
yes, I will. Let's call it an eigenvalue problem. So what we're looking for is a unit vector n and a scalar value lambda, so that if you take the stress tensor and multiply it by the unit normal, well, what happens if you multiply a stress tensor by a unit normal? You get that traction vector. And if we have chosen, if this unit normal is in an orientation where you don't have any shear stresses, then that traction is going to be parallel to that normal vector. Okay? And so we're looking for the unusual, unique normal vector where stress times normal is equal to some scalar times that same normal vector. So another way to say this is we're looking for a unit normal to a face where the traction vector is normal. Okay? You sort of follow what the strategy is there. And it turns out, you're being honest. Yeah. Okay, so this is actually a really common problem in mechanics.
Like where there's no shear stresses?
Well, for deform, we use this eigenvalue, eigenvector problem to find those principal stresses. But it turns out there's all kinds of problems that look identical to this, where you're trying to find a single vector and a corresponding scalar value so that the matrix times the normal is equal to the scalar times the normal. It comes up if you're trying to find axes of rotation of objects in dynamics. If you're trying to simplify calculations of moments of inertia in dynamics, and I'm sure a million other things.
Represent the matrix as a scalar instead?
Yeah, but you can't do it in general, you know, because if you think about this in general, if you take any old stress tensor and multiply it by any old normal, you're in general going to get 3 components for a traction vector. In this one specific case, or really 3 specific cases, you're going to multiply it by the normal, and you're going to get a traction vector that's parallel to that normal. And that's the special case that we're looking for. Okay. All right. And so let me just do one more thing. You can think of this, you can rewrite this as, it's the same problem, I'm just writing out the elements. So sigma xx, sigma xy, sigma xz, xy, yy, yz, xz, yz, zz, times nx, ny, nz is equal to, you can try this out, and you'll see that this is exactly the same thing. Multiplying this normal, this unit normal vector by a scalar is the same thing as multiplying it by this diagonal matrix. Whoops. Sorry. That would not. Sometimes I write things that make me shake my head. Okay. So it's all diagonal. And now you can rewrite it. This is the last thing I'll write, and then we're done. So now you can subtract the right side from both sides. Move this over to the other side, and you get this equation. On the diagonals, you have sigma xx minus lambda, and then xy, xz, then xy. Then on the diagonal, you have sigma yy minus lambda, yz, and then xz, yz, and then sigma zz minus lambda. All of that times that unit normal. And that has to be equal to 0. And if you want to find a non-trivial solution to this, that left matrix has to be non-invertible. Okay, so that's the mathematical setup. We need this matrix here to not have an inverse. And in order to not have an inverse, we need the determinant of that matrix to be equal to 0. If the determinant isn't equal to 0, you can come up with an inverse, and you get a trivial solution. But if the determinant is equal to 0,
Does the lambda, is it the same value for each of the?
yeah, that's just one single value. So we're looking for that lambda value.
Okay. the exact same.
The stress tensor. So
Oh, no, yeah, okay.
we're just so this problem is going to give us a set of 4 things that correspond: 3 coordinates for that normal, and a lambda value, and a single lambda value. And there are going to be 3 of those sets of 4 that solve this problem. Our new x, our new x-axis direction, our new y-axis direction, our new z-axis direction, and the scalars that correspond to those tractions. Okay, so that's it for today.